Hi everyone, welcome back. In this particular video, we're going to start talking about synthesis. And this video, in some sense, is a review of all the reactions that you've seen in the first semester of organic chemistry. So these are reactions of alkanes, uh, alkyl halides, alkenes, and alkynes. And depending on your instructor, you may or may not have talked about synthesis there, but this chapter sort of reviews all of that for you. So let's get started. The first sort of functional group or the class of compounds that you encounter in organic chemistry are alkanes. Okay. Now alkanes, these are just hydrocarbons, and these are saturated hydrocarbons. Which means they only have single bonds in them. Or it could be a part of a molecule which only has single bonds in it. Okay. Essentially, we are talking about a carbon that is sp3 hybridized. That is what we're talking about here. Now, as far as alkanes are concerned, the only useful reaction, I would say, like synthetically useful reaction, okay, synthetically useful reaction of alkanes is the free radical halogenation. And what this does is this reaction converts alkanes into alkyl halides. Okay, so if and essentially what happens here is, if you have an alkane, and if I want to represent represent the alkane by an alkyl group connected to a hydrogen, then what happens in this reaction is, when you react this alkane or alkanes, okay, when you react these with halogens X2 in presence of heat and light, then the alkane is converted into an alkyl bromide plus HBr. And so essentially what we're saying is that the hydrogens in an alkane are replaced by halogens. In fact, now I went too specific. The bromine could just represent a halogen. So we are using bromine as a representative example. And there is a reason why you use bromination, because recollect from the first semester organic chemistry that bromination is a selective reaction. And so that there's a reason why we use bromination. So bromination is a selective reaction. Okay, so an alkane, a hydrogen in an alkane molecule is replaced by a bromine essentially. So let's look at an example. So if we have a molecule like this, which is a butane, but it's a substituted butane. Okay, when we react this with Br2, in fact, I want to correct myself. Okay, the IUPAC name for this molecule would be 2-methylpropene, but this is also an isobutane, so that's why I called it a called a butane. Okay, so we have Br2 and HNu. Then what happens is the hydrogen at this tertiary carbon is replaced by a Br group. So we go from an alkane here to an alkyl bromide. Okay, now we said this reaction is selective. What that means is that when you have several hydrogens possible, okay, the reactivity order for undergoing halogenation is if you have benzylic or allylic positions, they are more likely to undergo a halogenation compared to tertiary, which is higher than secondary, and then usually primary or methyl is the least likely. Okay, so these are the hydrogens actually. So we're talking about the type of hydrogen in alkane when you have it. So benzylic or allylic, they would have the highest probability, tertiary next, secondary, primary, and then methyl. So again, just to sum it up, let's look at a final example here, very simple example. So if we have a molecule like this is an alkane. If we do a bromination on it, HNu and heat, this molecule here has primary carbons in it, or primary carbon hydrogen bonds in it. There's a secondary carbon hydrogen bond, there's a secondary position, and there is a tertiary positions. So there's primary, secondary, and tertiary, all possibilities in this molecule, but the major product that we get is the bromine at the tertiary position. Okay, so that's the reaction of alkanes, the free radical halogenation. In the next slides, or the next set of videos, we will talk about reactions of alkyl halides. Now that we've converted alkyls into alkyl halides, we'll talk about the reactions of alkyl halides and then move on further. Hello everyone. So to continue on, we'll be talking about the chemistry of alkyl halides here. And alkyl halides are molecules that contain a halogen as a functional group. Now in this particular segment, and even in the first semester of organic chemistry, we generally talked about alkyl chlorides, alkyl bromides, and alkyl iodides. And the reason, because fluorine, although it's a halogen, the reactivity of alkyl fluorides is not, does not parallel, or it's not similar to those of the alkyl chlorides, bromides, and iodides. They are very stable compounds. They do not undergo the sort of reactions that we talked about in the first semester of organic chemistry. So it's mostly the alkyl chlorides, bromides, and iodides that we'll be focusing on. Now, alkyl halides, okay, Rx, which represents an alkyl halide, these undergo two kinds of reactions: substitutions and eliminations. Now, as you may recall, there are two mechanisms for substitution reactions, which are called SN1 and SN2. And there are two possible mechanisms for an elimination reaction, and these are called E1 and E2. Now, you might also recall that SN1 and E1 okay, these occur simultaneously. And it's difficult to separate these out. Okay, so difficult to tease apart these reactions. Okay, and so for that reason, as far as synthesis is concerned, because the theme of this topic here is synthesis, we will focus mainly on the SN2 and E2 reactions. Okay, the mechanism of these reactions is beyond the scope of this video, so I will not be discussing that. If you have any doubts, please refer back to your notes from the first semester of organic chemistry. Now, SN2 reactions, as you may recall, these are bimolecular reactions. Okay, and this involves the reaction of an alkyl halide. Now I'm going to draw the alkyl halide slightly differently. This is still an alkyl halide. Okay, so there's an R group, there's a CH2 here, and there's the X. So that's what this is. So this is basically RCH2X. That's what I've drawn up there in a bond line notation. So if the SN2 reaction involves the reaction of an alkyl halide with a nucleophile. And this nucleophile is usually a strong nucleophile. So I'm using this negative charge to sort of symbolize that we're using a strong nucleophile. And what happens here is that the nucleophile goes and attacks the alpha carbon of the alkyl halide. The leaving group, which is the halogen, is kicked out. And so we end with the nucleophile now connected to that alpha carbon plus the halogen lost as the halide ion. Okay, so this is our leaving group, and we've made a product. So notice how what happens here is that the nucleophile gets connected to the alpha carbon. So this is the alpha carbon, and that gives us the product. Now, important thing to remember here is that this reaction proceeds with inversion of configuration, and this matters most when the alpha carbon is chiral. Okay, that's when it matters most, this inversion of configuration. Sorry, there's only one L here. Okay, so that's the SN2 reaction. So it's a substitution where the alkyl halide can be converted into pretty much whatever other molecule, because you can imagine that you can start with an alkyl halide and you react this with hydroxide, and your product is now going to be an alcohol. Okay, or you can react the alkyl halide with an alkoxide, and the product that you get is going to be an ether. Or you can react it with a cyanide, let's say, and you will get a nitrile as your product. So depending on your nucleophile, you get a variety of functional groups in your product, because you're just replacing that halogen with your nucleophile. Okay, so that's sort of short summary of the substitution reactions of alkyl halides, and we're focusing on SN2 reactions because they can be you have more control. Okay, you can favor SN2 reactions over E2 reactions. Now, again, important thing to keep in mind here is the order of reactivity for SN2 reactions. I think this is very important. Okay, so the order of reactivity, and this is as far as the alkyl halide is concerned, okay, your methyl halides, they are the best at doing this reaction. Then you have primary alkyl halides, and then secondary, and then tertiary. Tertiary do not react. So you cannot do an SN2 reaction on a tertiary alkyl halide. For a secondary alkyl halide, this reaction is already slow. Okay, so this is the fastest. And you might recall that this order, the reactivity order, is because of the backside attack. Okay, that's what leads to this reactivity order. So that's something else to keep in mind. So that means we can do SN2 reactions really well on methyl halides, primary halides. Secondary halides are possible if we control the conditions. Okay, so in the next slide, we will talk about elimination reactions of alkyl halides. Moving on to the elimination reactions, and specifically the E2 reactions of alkyl halides. Okay, E2 reaction of alkyl halides. The reactivity order here, and again, this reactivity order is with respect to the alkyl halide substrate. Okay, the reactivity order here is tertiary alkyl halides are the best. And then you have secondary, and then primary, and then, I mean, there's nothing for methyl actually, so I'm going to erase this. There's no elimination possible for methyl, but that's the reactivity order. So the tertiary alkyl halides, these are the most reactive, and primary alkyl halides, these are the least reactive. Okay, now the E2 reaction, again, if I draw an alkyl halide, and this time I'm going to draw the alkyl halide again slightly differently, because the E2 reaction involves what's known as the beta hydrogen. Okay, so as far as the halogen is concerned, or the alkyl halide is concerned, this is the alpha carbon and that's the beta carbon. So in an E2 reaction, the alkyl halide reacts with a strong base. So it's a base that it's reacting with, and this base is usually a strong base. So bases like alkoxides, those are strong bases. So the base, and I'll draw the negative charge in again to symbolize the strength of the base. So the strong base reacts with the alkyl halide. It deprotonates or abstracts the beta hydrogen. Electrons from that bond fall into the space between alpha and beta carbons, and the halogen is kicked out. Now, I did use a primary alkyl halide here just to show what the reaction looks like or the mechanism looks like, but we will talk about other examples. And so in the end, what happens is we get a double bond. We get an alkene as our product, plus we've got the base, which is now protonated, and plus we've got the leaving group that came out as the halide. Okay, as I mentioned here, I used a primary alkyl halide just to show the reaction, but we will look at some examples now. Things to keep in mind as far as the E2 reaction is concerned. Okay, so when we are doing a reaction, I will use some specific examples here. So let's say we have the alkyl halide, and let's use the alkyl halide that we synthesized when we did the reaction with alkane. So if we use this alkyl halide, and if we use a base that is like a small strong base, okay, or not a bulky base, let's put it that way. So I use sodium methoxide as an example here. Then we will get the more substituted alkene as the major product. Okay, this is the more substituted alkene that's possible here. How do I know that? Because for this particular alkyl halide, it has, that's the alpha, this is the alpha carbon. It has two possibilities for beta carbons. There's beta, this is also beta. Beta carbon is anything that's connected to the alpha carbon. Okay, and we have a beta prime carbon. And when I compare the beta carbons versus the beta prime carbon, I notice that beta prime carbon is the more substituted carbon because this carbon is secondary in nature, whereas the beta carbon is primary in nature. And so when the double bond is formed, or when the alkene is formed, the double bond forms between the alpha carbon and the beta prime carbon because this is the more stable, the more substituted alkene. Okay, so the more stable or the more substituted alkene is the major product. We call this a Zaitsev elimination. Okay, so this is a Zaitsev elimination, or the product is called a Zaitsev product. Now, it's not that the less substituted alkene is not formed. Okay, so this is the major product. And along with this, we will get some of this less substituted alkene, which is going to be the minor product. Okay, that's the minor product. So this is by using not a bulky base, whenever you're using not a bulky base for doing this reaction. On the contrary, now, if I start with the same alkyl halide and I use a bulky base, so again, we can use potassium T-butoxide as a bulky base. If we use that, then we still get both of these products. Okay, but the product where the double bond is formed between the alpha and the beta carbons, which is the less substituted and less stable alkene, this is now the major product. And the more substituted alkene, and which is also the more stable alkene, that is now the major, that is now the minor product. And this reaction is called a Hofmann elimination or a Hofmann reaction, and the product is called a Hofmann product. So with E2 reactions, we have two possibilities. We can either make the less substituted alkene or the more substituted alkene by choosing an appropriate reagent. That's the key. Okay, by the choice of the reagent. Okay, the choice of the reagent is what matters here. Choice of reagent, and by reagent I mean the base. By choice of the reagent, we can make either the less substituted or the more substituted alkene as the major product. Okay, so let's look at another example here. So let's say if we have an alkyl halide like that, if I do a reaction with sodium methoxide, okay, which is just a regular base, then I will get the more substituted alkene as the major product. Okay, this is major. I'm only drawing the major product here. If I do a reaction with potassium T-butoxide, then I'll get the less substituted alkene as the major product. Sorry, I don't know if I don't recollect if I misspoke, but when we use a regular base, not a bulky base like sodium methoxide, the more substituted alkene is the major product. When we use a bulky base, then the less substituted alkene is the major product here. Okay, so there are two possibilities and we have some control. So basically, as an organic chemist, I can choose which product am I going to make. Do I want to make the less substituted alkene as the major product, or do I want to make the more substituted alkene as the major product? Okay, so basically so far what we've done is we've seen reactions that convert alkanes into alkyl halides. Starting from alkyl halides, then we saw how we could do substitutions or we could do eliminations. Now the elimination reaction of an alkyl halide gives us an alkene as the major product. So in the next set of videos or the next set of slides, we will be seeing reactions of alkenes. What can we do with alkenes? That's what we will be looking at.